sort of tube thing up here in the upper right-hand corner. At 7 million volts, you would have discharge everywhere into the atmosphere. So they put it in this pressurized container, and they put a special gas in there, sulfur hexafluoride, which is a good insulator and keeps discharges from happening, so that you can basically have a source in the back here where you create your ions, and then you split the 7 million volts up over a bunch of parallel plates, and there's holes in them so that the charges you create can be accelerated through them, and then they come out here, and for this is a Czechoslovakian accelerator. They just happen to have the best picture. They use deuterium, which is mass 2 hydrogen or mass 1 hydrogen proton beams. Bring it out into this large magnet, and it's all in a vacuum system here. So all these tubes right here are under pretty good vacuum, and depending upon the direction of the B field and the magnitude of the B field, they can bend and focus the beam down one of these tubes, which then go down to your target chamber, where you can use the beam for studying whatever interactions you're interested in studying. And the ones we're going to talk about today are nuclear reactions. Now, this is sort of a low energy version of nuclear physics. A higher energy, they have a cyclotron, which is a different kind of accelerator. They can have a synchrotron, which is another. And these things get bigger as I say the words in size. So a cyclotron might fill this room that you see here, and a syncocyclotron might be a mile long. And then the version that you get of it that's in CERN is 20 some miles in circumference. So the biggest energy you can get here for singly charged ion beams, protons, is about 7 or 8 MeV. The one in CERN is 10 TeV. That's about 1 million times higher kinetic energy.
Is that the cyclotron or cyclotron?
It's a synchronous type thing. So what that means, so a cyclotron has 2 halves. One's positive and the other's negative, so that ions are attracted from the positive ions are repelled from the positive side and go to the negative side. When they get there, you flip the sign of the charges on them, and so they go back, and every time they do, they increase their energy by the amount of the voltage drop across. And they keep going back, and you put them in a magnetic field so they circulate back and forth, and when their orbit gets large enough, they leave the cyclotron at the prescribed energy. The one in CERN, they have a tube, and they might have a little area right here that I'm indicating near the accelerator here. And this might be turned positive right when the protons are in the middle of it. So they're repelled out towards the next ones, which were negative. When they get right here to the negative, you change it to positive, and you make the next one negative, and then they're accelerated through again. And so you keep accelerating them through these links round and round until they finally hit the energy you want them to have. And then they some funny relativistic things come in. You think you filled the whole accelerator with the beam, but from the proton's point of view, they're little pancakes of protons because of the Lorentz contraction. And so when they interact, there are these two pancakes of protons interacting with each other. So a lot of interesting relativistic effects in them. And the one in CERN has almost 10,000 superconducting magnets. And when one of those goes bad, they blow up. And so they had one of those accidents about 7 or 8 years ago, and it took them a year and a half to fix the accelerator and get going again.
Wow.
So, and those magnets are all very specialized. So we had a student here whose father was a plasma physicist in Switzerland. And he was talking about, if you're ever looking for a job, he said, learn how to make magnets. He said, the magnets that they order, say for CERN, take about 5 years to design and test. And they're not all the same magnet. There's probably 40 or 50 different kinds of magnets there. So you can make a lifetime job for yourself by learning how to make one kind of magnet that people need and assemble and test it and install it. So when you ask where are the jobs, there are always magnets. All right, today we're going to look at these collisions and some of the nomenclature that goes with them, and then we're going to try some of these problems out of chapter 14. So you're going to need a couple of things. You're going to need what was it called? The Excel chart that I titled Chart of Nuclides A. You're going to need that for getting masses of particles, and you're going to need your textbook. So if you don't have that, you might get it quickly. If you don't, you should have already downloaded that chart of the nuclides. If you haven't, it's on the Dropbox. All right, so here's what an encyclopedia calls a nuclear reaction. Change in the identity or characteristics of an atomic nucleus induced by bombarding it with an energetic particle. Bombarding particles might be alphas, gamma, neutron, proton, or heavy ion. In any case, the bombarding particle must have enough energy to approach the positively charged nucleus to within the range of the strong nuclear force. So this means that when you bring a projectile into a target, if you want to have a nuclear reaction, these things almost have to touch because the nuclear force is a very short-ranged force. So when we calculate, since it's an approximate thing, we just assume that these are just barely going to touch, and then it's possible for a nuclear reaction to take place. Doesn't have to happen. You can have Rutherford scattering. You can have other things taking place. As a matter of fact, when the astronauts went out to the moon and back, they would report seeing flashes of light in their eyes, but people who were looking outside or around could see no flashes when they reported it, and no one could see flashes when they reported it. And so they decided this was something happening in the eyes of the astronauts. And the description of what was taking place was that a high energy proton was coming through the chamber, through the capsule, and going through one of their eyes. And when it did, it hit a nucleus, and its local speed was higher than the speed of light in the nuclear material. and that produced Cherenkov radiation that would come out and be seen. But the Cherenkov radiation wasn't the normal blue glow of the nuclear reactor core that you see. And in fact, what happened was the shock wave that's the Cherenkov radiation became a front to project particles out into the eye and cause fluorescence. So that was the explanation given. So it was basically a nuclear reaction in their eye that they were seeing. First nuclear reaction was identified by Ernest Rutherford. He set about to do it, and he understood what he got when he saw that it happened. And that was to take an alpha particle from one of his radioactive sources, bombard nitrogen, and look at what came out. And what came out was a proton and an unusual isotope of oxygen, oxygen mass 17. Now, a couple things about this. I haven't put in the atomic numbers, the Z values. So the Z for helium is 2. What is it for nitrogen?
Is it 7?
It'd be 7, right? And so we'd have 9 protons on this side of the reaction, and we've got to have 9 protons on this side. So we've got a hydrogen, and what's the atomic number for oxygen?
16?
8.
Or no, sorry, yeah, 8, my bad.
8. So 8 and 1 gives us 9. So we've conserved the proton number. We have to have that happen. And the atomic mass, although the small amounts of mass that we deal with aren't going to change the atomic mass numbers, the atomic mass energy itself is conserved, but the atomic mass in detail is not. But the atomic mass numbers are. So on this side, I've got 4 plus 14, that's 18. And on the right-hand side, I've got 1 plus 17 is 18. So I have that balance. The chemists love to do this part of nuclear physics because it looks like chemistry to them. They add up things on the left side and things on the right side, and they're conserved. All right. The first person to create their own projectile and create a nuclear reaction were Cockcroft and Walton. And they figured out how to make a high voltage power supply. And their reason for doing it was they wanted to build an accelerator. And so theirs was the first nuclear accelerator used for nuclear physics. And they accelerated protons into a lithium-7 target. Lithium is atomic number what? These first up to neon are worth knowing.
3.
3. So I've got 1 plus 3 here. So over here I've got 2 plus 2. So that balances. I've got 1 plus 7 is 8. And I've got 8 here. So the reaction that they get was a fission reaction. And it split the lithium into 2 equal masses, both of them alpha particles. Cockcroft and Walton got a Nobel Prize for their work. Rutherford got a Nobel Prize for his work on Rutherford scattering mostly and creating the idea of the nucleus. But he figured out what an alpha particle was. He did the first nuclear reaction. He figured out the size of the nucleus. He figured out a whole lot of things about nuclear physics. And some people thought he deserved to get a second Nobel Prize for that, but he didn't. Who are the only two people to get 2 Nobel Prizes? Do you know?
But Marie Curie is one of them.
Marie Curie, right. She got a chemistry and a physics.
And here's another guy who got, is it physics and peace or chemistry and peace, something like this, right?
Nope. Got 2 physics. One for the discovery of the transistor and one for the explanation of superconductivity.
Didn't
All
three
right.
people find?
Yeah. I'm sorry. Who? I didn't hear that.
Didn't three
Pauling?
Didn't 3 people make
Linus
transistors?
Pauling?
Pauling?
Linus Pauling only, maybe, did he get one for peace? He might have gotten one for peace. Marie Curie should have gotten one for peace. She really should have had 3.
Oh, it's. I just looked it up. Only person to be awarded 2 unshared Nobel Prizes, 1 in chemistry and 1 for peace.
Okay. Was
Linus
Pauling.
Pauling.
Yeah.
Should be one of the BCS person, right?
Yes.
Is it Cooper?
Cooper. No.
Bart?
Let's see. It's the B.
Bardeen?
Bardeen. Yeah. Bardeen. Thank you. All right. Let's take a look at the lithium reaction first. When you have these reactions and we look at mass energy conservation, there is kinetic energy brought into the collision over here, and there are kinetic energies on the collisions over here. So we group all those kinetic energies together as Q. So Q represents the kinetic energy of the products minus the kinetic energy of the things, of the reactants that came in. And it's considered an exoergic. Thermoergic is not used with the nuclear physics because there's so much energy involved in one of these. It's not thermal in any sense of the word. But usually we just talk about Q being bigger than 0. All right, so let's take a look at what goes on here, just the mass energy. So I'm going to try to calculate Q. To do that, I need the sum of the masses on this side and the sum of the masses on this side. So I want you to check your chart of the nuclides Excel spreadsheet, and let's see that you agree that I've got the right lithium mass here.
It looks right.
Okay, good. So if I add up the mass of the proton and the lithium, I get 8.023829. If I double the mass of the helium, I get 8.0052. So I want to calculate Q. So Q is going to be equal to the mass of the reactants minus the mass of the products. And so that'll be the 8.023 minus the 8.05. And then I'm going to convert that with this conversion factor, and I get 17.35 MeV, and it's positive. So what does the positive mean?
It's exoergic. How do you say the word?
It naturally happens.
Exoergic.
Exoergic.
Yeah. So what does that mean?
Doesn't that mean it naturally happens without
It could naturally happen, yes. So it means that if the two are together, there's a lower energy state for them, and that's as two alphas, and there's lots of energy left over in the process. So it means that the kinetic energies of these things is much bigger than the kinetic energies of these things. That doesn't mean that you can just put lithium and hydrogen together and you're going to get a nuclear reaction. What was that other part of the definition? The bombarding particle must have enough kinetic energy to approach the positively charged nucleus and touch it. Can you bring a proton and a lithium nucleus together so that they just touch with a couple of EV of energy?
No.
How much would it take?
Couple MEVs.
How would you calculate that?
For that Q equation down there?
Nope, that won't help you. Well, before we get to that answer, let me go down here and talk about some nomenclature. When you've got the mass, when you've got your particle, your projectile colliding with your target, you're going to have a small mass and a large mass often that result. So our projectile here is the proton hitting the lithium atom, and we produce two identical masses. So there's no large and small there, but that's just one of those oddities with alpha particles that happens. We can write this as projectile on a target yields a large and a small mass. And so the target, the two large masses are in parentheses, and the incident projectile and the small mass product are outside the parentheses. So let's take a look at that. So this reaction would be written as a P lithium 7 helium 4 alpha reaction. Now, since the two are the same, it could be that you could just put 2 alpha here and nothing outside, and some people do, or you can put an alpha inside and outside. But you wouldn't put 2 alpha on the outside. You want to have 2 things in the parentheses. And this would be called a P alpha reaction or a P2 alpha reaction. All right, so how close does a proton have to get to the target nucleus for the reaction to take place? Well, over here we're looking at the reaction that's somewhat related to what Rutherford did, but not quite. And they're mentioning here that there are all kinds of different results that can happen from this nuclear reaction. So this would be a proton on nitrogen 14, which when it goes inside turns the whole combination to oxygen 15, which then could become a neutron with oxygen 14, so that would be a PN reaction. Or it could be become an alpha with carbon 11, which would be a p alpha reaction, or it could be become a deuterium nucleus with nitrogen 13, which would be a PD reaction. Or you could even get 3 particles. And so the nomenclature is not clean for anything, excuse me, anything more than 2 reactions. Products, excuse me, more than 2 products. So how close does the proton have to get to the target nucleus for the reaction to happen? So the idea is that the nuclear force doesn't extend much further than the size of the nucleus. And much further means not much further, maybe 1/10 of the radius or so. So by saying that the reaction takes place when the 2 touch isn't exact, but it's a repeatable idea that everybody can agree on. So when the projectile comes in, when it finally just touches, then it's possible for a nuclear reaction to take place. Well, remember that the radius of a nucleus is 1.2 femtometers times a to the 1/3. So that means our proton is 1.2 femtometers, and our lithium is what? What's the radius of lithium?
.73 femtometers.
1.73 femtometers, okay. And its atomic number is 3. So the kinetic energy that you need to get that projectile right here with no more kinetic energy, so it stops right there, is just the potential energy that it has. So when the projectile turns all of its kinetic energy into potential energy so that they're just touching, this is the kinetic energy it has to have. And so that, for our problem, will be 1 times 3 on the top over 4 pi epsilon naught r sub p plus r sub t. So can you work out that number for me? Just as a reminder, the charge of the electron squared over 4 pi epsilon naught is equal to, gee, I want to say 1.1 EV nanometer. Oh, it's 1.41 EV nanometers, I think it is. So can you stick in those 2 values for the radius, the 1.2 and the 1.73 femtometers, and divide that into 3 times 1.41 EV nanometers.
What did you say the value for 4 pi epsilon naught was again?
E squared over 4 pi epsilon naught was 1.41 EV nanometers.
It'd be a large number.
How many MeV?
I got 6.096 times 10 to the 14th.
Yeah, that one doesn't sound quite right, does it?
I plugged in 1.41 EV nanometers. Right.
Okay.
My
I got
numerator is 1 and 3. 1 times 3. And my denominator has 1.41 EV nanometers times. Then the 1.2 times 10 to the minus 15 plus 2.295 times 10 to the minus 15.
No, the 1.41 EV nanometers should be in the top, right? Not the
Yeah.
denominator.
Oh, that's why.
Let's see here.
So you should get something in MEVs.
Wait, what is femtometer again? 15.
10 to the minus 15. Nanometers,
Okay.
10 to the minus 9.
Yeah. Oh, I got something massive.
Lay it on us, bro.
I got about 1 MEV. Remember that 1.41 is EV nanometers. And you're dividing it by femtometers, so you should get a 10 to the 6. And that leaves you with 1.41 times 3 divided by 2.95.
Did you get 1.43?
Sounds fine.
Oh, let's go!
All right.
I got like 2.04.
Okay, so you guys you're working with the division of numbers right now. You've got the orders of magnitude right. So we're talking about something with 1 to 2 MeV kinetic energy, just to make it in so a nuclear reaction can take place. So when that reaction takes place, Q was the difference in the mass energies of each side. So if you bring in any kinetic energy, that adds to the Q of the reaction and gives you still that a tremendous energy of the 2 alpha particles coming out. So the interesting thing here is you bring in a 1 MeV proton, and what do you get out? You get out some 7 MeV or 8 MeV alpha particles. That's almost magical, isn't it?
It is.
You get so much energy coming out of the reaction, so much more than what you put in. So we did this experiment when we went to Texas a few years back. We used lithium fluoride because fluorine turns itself into an alpha particle also. And it's even higher in energy, almost 25 MeV. But the probability for these things happens is small and we would collect data for an hour and get one event, one particle detected. And that was all we had time for. But it was always at the right energy because there was no background at all. It was an interesting experiment to do because of the low counting statistics. I mean, when your peak has an area of 1, it's not an overwhelming experimental result. Now, if we take, so you can do this for any of these reactions to get an idea of what kind of energy it takes. And that's, if you're going to do an experiment, you have to know beforehand if anything can ever happen. So with Rutherford's experiment, protons are the easiest thing because they bring in only one charge. Once you put in 2 charges, that doubles the energy of things. So fortunately for what he was looking at, a 5 MeV alpha particle was enough to make it into and give a nuclear reaction. The other thing that was interesting was that the reaction he wanted to look at was exoergic, that it was going to take energy. So not only did he have to have enough energy to get them to touch, he had to have enough energy left over to provide to the system to convert it into the mass of the products. So, sometimes you just need a little luck when you do some of these things, no matter how smart you are. So, and this is done the same way. The before mass is, the mass of the reactants is 18.05 for the helium on nitrogen, and the products of a proton and an oxygen come out to be slightly higher mass. And so you've got to bring in kinetic energy to make that mass go up. And that's pretty much what it says here. You had to bring in 1.2 MeV of energy. So whatever energy it took for the helium to get in and just touch the nitrogen, you had to have another 1.2 MeV left over of your kinetic energy to make this reaction happen. I hate that. I just don't like that. It's a chemist drawing, and it's just not good. So, here's some samples of energies that you should try to calculate a couple of these, and you've got the masses now. When they've got an M here, their mass is larger than their ground state mass. So you're not going to want to do these. They're metastable states. So they're in an excited state, and they're going to decay to a ground state with the emission of a reasonable amount of energy that you have to know. So if you'll deal just with the ground state interactions, you will be much happier. So try a couple of these, explain then what this energy threshold means, and we all know what natural abundance is, so we don't have to worry about that. All right, so we could set this up right now. If you've got your spreadsheet open.
I gotta get mine real quick.
I got it open.
Okay, so go down to mass 52 for chromium and manganese. So the third column is the mass number.
Okay, mass 52, you said?
Yeah.
Okay.
I'm on it.
Got it.
So what'd you get? for the real mass of chromium. So
is it 51.98221?
chromium is atomic number 24, and manganese is atomic number 25.
So for chromium, real mass is 51.94.
51.94. Now, yeah, go ahead.
Well, 51.94 to 05.
Okay, and what's manganese? Atomic number 25.
Let's see here.
Same mass.
51.94557.
Okay. So that's what you're going to need. How many digits do you have to have?
I'm assuming all of them that are listed here.
All right. Let's see, did I write this out?
10 digits.
All right. Right here.
7.
When we, these are different in the third decimal place, right?
Yes.
But if you want 4 significant digits here, that means you've got to have 4 significant digits starting at the third decimal place. So if you only want 2 digits over here, then you only have to go to the, to this decimal place. But usually you want to get 1 or 2 past that. So that implies you've got to go this far. And typically that's what we keep, are 6 decimal places. People get put off by that. They think you're just piddling down with small things. But you tell them, look at this, if this is a nuclear reaction that is with fission, in this decimal place is where you start to see the energy from fission. And yet that's what runs 20% of all our electrical production in this country. So don't tell me that this digit isn't important or that digit isn't important. People just...
Dr. P, did you make this whole spreadsheet by yourself?
Yeah.
No, I had 4 work study students who helped.
You had the Butch boys do it.
It took 2 semesters to do it.
Jeez.
I didn't have 4 the second semester. Yeah. All right. So this will give you an idea of what we mean by the energy above threshold, how to calculate these energies. Well, what do we want to do with that? So I want to go back to something, the binding energy equation that we had. And, you know, it's nice that you can calculate the binding energy of all these isotopes. And as you add more particles to them, each particle brings in its binding energy. So the binding energy of a whole nucleus just gets bigger and bigger by leaps and bounds as you add more and more particles. But there is a question about, well, what's the average binding energy? You know, if you've got 20 MeV of binding energy and you've got 5 nucleons as opposed to 10, the one with 10 nucleons doesn't have much binding energy per nucleon compared to the one with 5 particles. And so the idea was, well, maybe we can see which elements are the most strongly bound, the ones with the most binding energy for each particle in the nucleus. And that ends up being iron. And that has all kinds of consequences. One is a normal star that lives off of proton fusion will build up all these elements by fusion up to iron, but you can't go past it. Now, how do we know they don't have any iron in them? Well, all those heavy things seem to percolate up to the surface in stars, and you can see the atomic spectrum of those elements in the stars. And we see all of them. As a matter of fact, that's how we discovered helium, was in the spectrum of the stars. That's why it's called helium, for Helios. We see all these elements. What we don't see in a normal star are all these elements, the heavy ones above iron. And there's a reason for that. You can't make them by fusion in a star. So how do you make them? You make them in a supernova. So what happens right before a supernova takes place is you've got a star that's turned itself mostly into carbon and other heavier elements and a lot of neutrons. When it blows apart, all those neutrons start interacting in a nuclear event with the heavy elements, the carbons and the irons and such that were in the star, just stuffing them full of neutrons. So it takes their atomic mass way up here, and then they start beta decaying backwards to become different elements. So the fact that our Earth is full of heavy elements says that our planet was made up of the debris from a supernova that coalesced into this rocky planet. Now, if you've got an element out here, and let's say you've got 240 particles, and you make it split in half to some two nuclei that have 120 particles each. Is that an exergic reaction, or does it take energy to make it happen? Well, think about all the energy you have here. You've got 240 nucleons times this average binding energy. Over here, you've got 240 nucleons with a higher binding energy.
I would imagine it takes energy.
So it takes energy to increase your binding energy. So this can happen. But putting these two together to go up here, you've got to provide all that mass energy because it has less binding. So this is the binding energy. So this is a more stable nucleus than this is. So fissioning out here to products is possible. Taking these products and having them naturally fuse together to form something heavier doesn't happen without a whole lot of energy coming in. So fission here produces energy. Well, what about over here? Well, it's just the opposite here. You're going to the more bound states here. So these are the least bound. And so fusing particles together produces energy. So what about these little spikes? So if I'm going from low to high is what's possible. What's this process right here? Low to high. It's going to produce energy, isn't it?
Yes. So fission?
It's a fission. And our idea of a commercial fusion reactor is one that fuses things together to produce lithium so that you can fission back and get some more energy out of the system. And you'll end up here. So the real trick is you have hydrogen fusion that produces energy in a neutron. And the neutron comes out and interacts with the lithium mirror you've got, and that fuses the lithium mirror into 2 helium, so you get energy from your mirror system, and it sort of doubles the effect of the fusion interaction. So you can take a fission and a fusion and an event are just another nuclear reaction. And you can take any combination you want to see how much energy comes out. The ones that happen most often are the ones that produce energy. All right, that's all the time we've got today. Sorry we didn't get to work any more problems than we did. But give these a try. They're all exactly like the problem you just worked. It's a matter of looking at the balancing of equations. You bring a proton into lithium, who says it can only produce 2 alphas? Why couldn't it just stay as a single nucleus? Or why couldn't it turn into a lithium 6 and a deuterium, for instance? There are all these other combinations that you can look at and ask, are these possible? And that's an easy one to look at, is the proton on lithium. There's only 3 possibilities there, and they're worth looking at because they became the point of contention. Something similar to that became the point of contention when cold fusion was discovered, and people were sort of miffed at the idea that that it pitted the physics community against the chemistry community. And really nobody won. The physics community was right, but nobody won because everybody was right. And there was no such thing as cold fusion. All right, guys, that's all for now. Be sure to kind of catch up on all the homework. And I didn't get many submissions, so get some of that stuff to me.
Thank you.
See you guys later.
Yes, sir.
Thank
you.
Bye.
Thank you.